computer, and then I'll give you the. All right. Well, that's going to be the introduction to the video. Is that
totally fine
statement that I made? Okay, James, take it away, please.
All right, thank you so much. You need to give me the ability to share.
I will give it to you. I'm just going to make you host because I don't know how else to do it.
Yeah, I won't do anything bad, I promise.
No, I don't. You can do it as bad as you want to. Please.
All right, perfect. Okay, so thank you so much. Before I get into the slides, I want to give you all a chance. I'm going to show some demo code at the end of this talk. All of it is available on my GitHub. If you go to github.com/jameslam/talks, you can find this one. So I like to show that at the beginning so you can see and copy it down. These slides will be shared later, and so will the link. Okay, let's get right into this. So my name's James Lamb. I'm an engineer at a company called Saturn Cloud. And at Saturn Cloud, this is going to be the only like marketing-y slide, I promise. At Saturn Cloud, we work on a managed Dask offering. So if you've ever used, say, Databricks for Spark or Cloudera for Spark or something like that, we offer the same sort of thing for Dask. And really, this is like an integrated environment for doing data science work, for doing machine learning, for doing exploration, visualization, using Dask. So the thing that we know really well at Saturn is using Dask and Jupyter and some of these other tools like Prefect together. So just disclaimer, I work at a Dask shop, and it's one of the reasons I fell in love with Dask. In this talk, before I skip ahead, let me tell you what we're going to talk about. So in this talk, I'm going to describe practicing machine learning on Dask. I'm going to teach you a little bit about what Dask is. This talk assumes no prior knowledge of Dask at all. We'll talk about machine learning on Dask generally, and then in the second half of the talk, I'll show you some demos with the new shiny LightGBM Dask integration that a couple of people in the Dask community have been working on for a little while. I'll tell you about why I'm calling it new, and we'll go through those demos, and then at the end, I'm open to questions and answers, and I'll try to answer anything that I can. So with that, let's get right into it. Let's start with why Dask, before we even talk about what is Dask. Some of these logos should look familiar to you. For those of you in this meetup, if you're working in Python doing machine learning work, you've probably used scikit-learn or NLTK or pandas, or this library in the middle here, whose name I won't pronounce because I know that it's controversial. You've probably used some of these libraries, right? But these libraries broadly were designed to work only on one machine. They were really designed to work on one physical machine. So, if you have a lot of data, it's going to be hard to work with these machines. With these libraries. And I should say also, when I say a lot of data, I don't necessarily mean a lot of training examples or a lot of features. A lot of data in this space can also be a very large model. Think of something tree-based with like 10,000 trees or something, or very, very high max depth. It could also be a lot of experiments. You could be searching over like a big grid of hyperparameters, something like that. So when I talk about a lot of data and that being a limitation for some of these libraries, it doesn't just mean observational data. And this is kind of an experience that I've had before as a practicing data scientist. You have a big idea, you have a big data set, you're like, cool, I know Python. Wait, I only know Python. Like, what am I going to do? And before I continue, I want to make it clear to anyone who's thinking like, okay, well, that's not me. I don't really work with large data sets. I don't really work with large experiments. It isn't hard to blow out the available physical resources of just like a kind of standard issue professional data science laptop. There is this really good blog post and talk by Wes McKinney, the creator of Pandas, called 10 Things I Hate About Pandas. I really recommend that you look this up. You can find the blog post online or versions of the talk on YouTube, where he says, that for him, he is the expert of all expert Pandas users. He recommended back in 2017 that you have 5 to 10 times as much memory as the size of your data set when you're working in Pandas. And think about once you start using machine learning libraries, like say once you use XGBoost, which has its own data structure that takes additional memory, it's actually not hard to get in a situation where your laptop is maybe not cutting it. And so for these problems, you have a couple of options. And so one is to do the main machine learning work on your laptop, but to just decide that you're going to use less data or like a pared down version of that data. And there are tons of great tools for storing data sets that are larger, much, much, much larger than your laptop or your local work machine that let you execute queries that create some sort of smaller summary that you can pull back to your machine. And so those are, data warehouses like BigQuery, Snowflake, Amazon Redshift. Those are databases like Postgres, like MongoDB, like Elasticsearch. Those are query over file engines like Presto, Drill, Athena, Spark SQL, things like that. These things will all let you store more data than you can fit on your laptop, write a query or write a job, and have that thing prepare for you a smaller version. Maybe that version is aggregated, maybe it's randomly sampled, something like that. So that's an option. Another option you have is to do what, like clickbaity articles on LinkedIn will call scale vertically. And so that just means you can get a bigger machine. You can go to any public cloud provider. I've listed 3 here, but there are many more. And just like get a machine bigger than your laptop, shell into it, bring your data into there, do all the stuff that you love to do in Scikit and Pandas, and then shut the machine down. That's an option. But that option is going to cost money, and you're going to be paying for the capacity of that machine the entire time that it's provisioned. So when you're in that case, you have to provision for kind of the peak amount of memory that you're going to use. But most of the time, you're not going to be using that machine. So think about the max memory that you'll need for a training run with PyTorch or something. You're going to get a machine that's that big. And sure, some of the time on that machine is going to be spent training, but some of the time is going to be spent like copying apt-get install and yum install commands from Stack Overflow, or making plots, or not even looking at the machine and like going to get coffee or something. It's all going to cost you money. One other option that you have to work with bigger problems or bigger data is to use many machines. So instead of getting one big thing, maybe you'll use many machines. And there are lots of different options for this. So the general purpose ones, the ones that are really popular amongst a lot of data scientists, are Dask, Ray, and Spark. And Spark is kind of the established choice here. It has been for a while. Spark has been successful for very good reasons. We'll talk about Spark a little bit more in a minute. Ray and Dask are younger frameworks that have similar ambitions. There are also slightly more specialized use more machines sorts of tools that are specifically intended for data science work. And that might be something like Kubeflow or Amazon SageMaker, Google AutoML, something like that. These are kind of the options that you have. Downsample your data, get a bigger machine, or just use more machines. You may also find that when you're in that use more machines world, some of the machine learning frameworks that you like have implemented their own multi-machine training and multi-machine evaluation frameworks. So XGBoost, LightGBM, TensorFlow, PyTorch, if you go look in the repositories for these frameworks, you're going to find that they have kind of implemented distributed training almost from scratch. You're going to see stuff in the XGBoost and LightGBM repos that is like the primitives of MPI or socket-based parallel communication that you might have learned if you studied computer science or something like that. And so you may also find if you can say like, I can fit this problem into just TensorFlow or just XGBoost, you might find that you're able to use those frameworks. However, those frameworks for training models in parallel, they can be really limiting, right? So you're not going to tend to find in those frameworks a lot of options for doing like very sophisticated feature engineering in a way that is parallelized, distributed, and kind of efficient. You might not find very fine-grained control over data loading. You may find yourself having to do things like loading data up on a client machine and then moving it to all of these other different machines. And so 2 options that I think like are popular because they give you a little bit more control over the complexity, because they let you do more cool custom stuff, are Spark and Dask. And so I want to just go through a little comparison of Spark and Dask. I'm just going to tell you right now, I'm just going to disappoint you right from the beginning. We're not going to come out of this with you knowing my opinion on whether Spark or Dask is better. Just like every frustrating conference talk you've ever seen, the answer to this is going to be, it depends. But I hope to give you a little bit more nuance, about how and why it depends. So let's talk about the way that these are really similar first. So both Spark and Dask have distributed machine learning training libraries. So in Spark, you have Spark ML, you have MLlib. MML Spark is a project from Microsoft that lets you get access to LightGBM and to some other Microsoft machine learning frameworks in Spark. XGBoost publishes a jar for XGBoost for JSpark, which is the XGBoost JVM project with Spark specific interfaces. So you can train an XGBoost model on a Spark cluster on like a Spark SQL data frame or something like that. Dask also has high level machine learning libraries, and we'll talk about those more later. So both frameworks have that in common. They also both have distributed data structures. So in Spark, you have, the RDD has been a fundamental part of Spark from the beginning, but you have other data structures like the data frame and distributed matrix. Dask has these as well. It has arrays and data frames and other arbitrary collections. The distributed data structure is a really, really important piece of this puzzle. It lets you hold, say, your training matrix for a machine learning task. It lets you act on that matrix as if it was one thing sitting on your laptop, one thing that you could just like view in a browser or something, even when it's actually something that's split into many pieces that might be spread over multiple physical machines. So both Spark and Dask offer this capability. Let's talk about a few differences, a few kind of things that the Dask ecosystem will sell you as benefits of Dask over Spark. So the first big one is that Dask is a Python first framework. Dask is Python all the way down. I mean, I guess if you really say all the way down, it's as much C and Fortran as any other thing in Python is, but it's all the code that you write at the user level is only Python. So one of the difficult things, if you're used to Python, but you're using, say, PySpark to work with Spark, one of the difficult things that you've encountered is you change something, you made a mistake or something's broken, and you get this like gnarly 200-line Scala stack trace. And you're just like, what is this? I don't write Scala code. I barely even know that this is Scala code. Like, please help me. That's not going to happen in Dask. Dask is Python all the way down. That also means when you want to do highly custom stuff, you just write Python functions. And Dask will know how to, use Pickle or Cloud Pickle to move your data and your functions around. And it just, if you're only writing Python, it really, some of the friction that you'll find with PySpark is not there. The next benefit I want to talk about is API parity. So if you've ever had the experience of taking code that was not made to be distributed, code that was, say, in pandas, using pandas as a framework, and then turning that into something that can run on a Spark cluster, you've probably felt like you're writing Spark code, right? You're like, okay, what is a Spark data frame? Like, what is reduced by key? Like, what does it mean? Do I need to care about, people on the internet are talking about data being shuffled over the network. What even is that? Do I need to care? It doesn't really feel like that in Dask. So some of the core Dask maintainers are also core maintainers from pandas, from NumPy. Fine, I'm just going to tell you, I pronounce it NumPy. From NumPy, from scikit-learn. And so they've made the Dask APIs look and feel as close as possible to those libraries. It's not quite to the level where you can say like replace an import pandas SPD as like import dask.dataframe SPD, but it's pretty close. And so you can go pretty quickly from stuff that worked on your laptop to stuff that works on a Dask cluster. The next thing that's cool about Dask that Spark kind of struggles with is that you get finer grained control over the task graph. So when you're working in Spark, the dominant pattern in Spark is this, this set of functional programming primitives like map, filter, reduce, group by, things like this, where you kind of fit your program into apply a function to each element of an array or a matrix or something like that. Dask has a lot more flexibility. In Dask, if any sort of like flowchart, any sort of graph that you can think of code to be executed, you can express in Dask, and Dask will handle parallelizing that for you and kind of executing it efficiently. And then finally, Dask has first-class support for multi-dimensional arrays. So in Spark for a long time has not had support for multi-dimensional arrays. I wrote this slide about 3 months ago. I haven't like checked in on Spark to see if that's there, but at least as of 3 months ago, I did not see any support for multi-dimensional arrays in Spark. There are also some ways that Spark is maybe a better choice than Dask for some workflows. And the biggest one, like the big one that should be up in bright lights, is SQL. So if you've worked in Spark, you have probably used Spark SQL. I know that I did the first maybe 10 times I sat down to do any Spark stuff. Because Spark puts some guardrails on the computing, because they use those functional programming primitives, it means that they can offer a SQL engine. I'm not going to say easily. It's taken an enormous amount of work by a lot of contributors and like a lot of ongoing effort. But there's a path to creating and maintaining a very reliable SQL interface over data in Spark. That's not really been the case in Dask because Dask has, this like greater ability to customize and to do weird low-level things. So there are ongoing SQL over Dask data frame projects. There's a project called Fugue. One of its maintainers is here in the meetup tonight. There's a project called Dask SQL. There's a project called Blazing SQL. But these projects are not as mature as Spark SQL is yet, and not as broadly adopted. So if you're just like cranking through a bunch of tabular data sets with SQL, Spark is probably a better option. The next feature that Spark has that Dask maybe doesn't have as much of are high-level optimizations. So when you do things in Spark, that's like maybe you're going to map a function, and then you're going to do a group by some key, and then you're going to like add a bunch of stuff, and 10 layers down, you're doing a filter by with a list of specific keys. Well, Spark will know to take that filter by and pull it all the way to the beginning of your analysis and filter out data that wouldn't pass that filter right at the beginning to save computation. Because Dask has less guardrails, it doesn't have as many of those types of features. So if you're really, really performance sensitive, you can get into places where Dask needs a little bit more attention, where you need to work on it a little bit more. The next thing that Dask doesn't really have that Spark does is graph data structures and graph algorithms. So Spark has had this project called GraphX for a number of years. There are projects in Dask. I can't remember the name, but there is a Dask project that aims to be similar to the NetworkX library. It's not as widely used and as mature as GraphX. So if you're working only on graph problems, maybe Spark is a better choice for you. Full disclosure, I haven't tried the Dask NetworkX thing. This particular line was taken from the Dask documentation on Dask versus Spark. So if you know that Dask is actually really sweet for networks, I would like you to tell me that at the end of the talk. And then finally, Dask is Python first, which is awesome if you're writing Python. But if you have Java or Scala or R, which are the other kind of main languages supported by Spark, you're going to have a bad time. It's not impossible, but Dask as an ecosystem really doesn't put a lot of emphasis on, you being able to run your R code in Dask. They're really, really focused on the Python data science and data engineering experience. So there are a lot of reasons to prefer Spark to Dask and vice versa. Okay, that is all that I want to say about Dask versus Spark. We could talk about this forever, and also I'm not the most qualified person to talk about this. So if you want to read more in anticipation of these questions, the Dask developers have written this documentation on the Dask official website comparing to Spark, and there's more details there. And you'll also see that a lot of the bullet points on the previous slides, I basically just took right from there. Okay, that's the end of that. Now you've heard my pitch for why Dask. It does similar things to Spark, but it's all in Python, and that's cool. Let's talk about what Dask is. Let's talk about like how it works. And let me take a sip of water while you look at this Queer Eye GIF. Okay, cool. So Dask works great on a single machine. The first way that I learned Dask, I didn't even know that it could do kind of multi-machine computing. I thought that Dask was just like a library that let you work on a pandas data frame that was bigger than memory on your laptop. I thought it was like big memory or big matrix in R. And it does do that, and it's sweet. It can also be used to parallelize code on a single machine. You can use it in place of, say, like multiprocessing in Python or something like that. It works great. But I'm not going to talk about that for the rest of this talk. You're welcome to go investigate that on your own. So for the rest of this talk, I'm going to talk about using Dask to orchestrate data science work on multiple physical machines. But just remember, it does work on one laptop. Just pip install Dask and you'll be off. Okay, so Dask is not a library. I mean, there is a library called Dask, but when I talk about Dask in this talk, I'm mostly talking about this ecosystem of libraries, different libraries that do different things. And so you'll see this kind of like bright purple bracketed thing in my slide titles when I'm talking about one of those sub projects. Okay, so let's talk about Dask distributed. So let's start there. Dask is a workflow. You know, you describe work to it that you want one or more computers to do, and Dask makes the computers do the stuff. That's like the basic idea, right? And they've created these abstractions called the client, the scheduler, and the worker. This image comes directly from some Dask documentation. I credited the author because technically it's from a proposal to change Dask documentation, like deep in some issue or GitHub pull request. But for all intents and purposes, this is Dask maintainer documentation. Okay, so anyway, I'm getting distracted. Dask has these nice abstractions of client, scheduler, and worker. And you can kind of plug in different types of each of these. And so the client is code that you run, think like in a notebook or just in a Python session on your laptop. The client knows how to talk to something called a scheduler. So the scheduler knows how to go do work. It knows how to say like, okay, you told me to load this data from S3 and then to apply this function to add a new column to this data frame and then to group by this other column and take like the group by standard deviation. The scheduler understands how to turn those Python functions into a graph of work to be done. And we'll talk about that more in a second. And then the scheduler talks to workers. Workers are just processes. And it tells them like, okay, here's task 1, 2, 3, 4, 5. Like worker A, you're working on this. Task, 5. Worker 2, you're working on this, et cetera, et cetera. And this kind of separation means that you can plug in different things at different levels. So in the code snippet on this slide, I'm using something called a Fargate cluster, which we'll talk about later. That substitutes in the scheduler and worker as AWS Fargate tasks instead of processes on your laptop. And we'll talk about that as we continue. Okay, so one important thing, I think when you see these talks on any distributed system, it can be confusing sometimes what a worker is. So I want to be really clear that when I say worker in the context of Dask, worker does not have to mean one physical machine. You can run a 10-worker Dask cluster on your laptop. So a worker is just a process that you can kick off from the command line. If you pip install Dask, you can open 4 shells and run, Dask scheduler in one of them and Dask worker in the other 3. And you'll have a 3-worker Dask cluster running on your laptop. So keep that in mind that, worker is not always synonymous with physical machine. Okay, so how do you set up one of these clusters? How do you set up like a scheduler and some workers for your client to tell to do stuff? Well, there are a ton of options. There's, for example, if you already have an existing Spark cluster, whether it's one that you manage yourself or it's like Google Dataproc or EMR or something like that, you can use Dask Yarn. And Dask Yarn will use the Yarn resource negotiator as the scheduler, and it will spin up Dask workers on your kind of your data nodes and your Hadoop cluster or whatever it may be, and you'll be off. You can do whatever. If you're working in a high performance computing setting and maybe you're used to using something like Moab as your workflow scheduler, you can use Dask or Dask MPI, and that'll work great. If you're working in Kubernetes, whether that's microcreates on your laptop or one of the cloud managed Kubernetes options like GKE, EKS, AKS, all the alphabet soup, there are a bunch of projects. There's a Dask Helm chart that you can use to set up Dask. There's a Dask Kubernetes project that'll let you connect to kind of any Kubernetes cluster. And there's a project called Dask Cloud Provider. What Dask Cloud Provider will allow you to do is connect to other non-Kubernetes cloud services for running containers or like running workflows. So at the very end of this talk, I'll show you a demo using AWS ECS, which is a thing that runs Docker containers on AWS EC2 with no Kubernetes. It's just like good old Docker daemons. Okay, with that background covered, so now you've seen kind of, we have this structure of your code talks to a client. The client knows how to describe your code in a way that a scheduler understands. The scheduler knows how to describe your code to workers in a way that they'll understand, and it keeps track of what each worker is doing and tells them what to do next. Now I think we can talk about the task graph in Dask. So all of your work is ordered in a graph like this one on the right-hand side. You can think of each node in the graph as a Python function. Each of these circular nodes as a Python function. Each of these square nodes, those are data. So data are either inputs or outputs. And then the edges describe a data flow. So either into or out of a function. That's like the basic idea here. And there are 5 steps in constructing the graph. The first is construction. And this is where you just take all your Python functions, put them in a dictionary. Like Dask does this in a very structured way. You never have to build this dictionary yourself. And that just describes kind of what's going to happen, the order and which things depend on which other things.
Hey, James.
Yeah.
Sorry to interrupt you. Could you just take a moment and click admit all on if you have, because I think yes. Sorry, I wish I could keep an eye on that for you, but
Totally fine. I forgot, you know what? I forgot that I became the
yeah, I did too.
Sorry about that.
We've got some folks there.
Yeah, if you see that again, interrupt me anytime.
I don't have them. But I think we're late enough into it that this last click should be fine.
Okay, I think we're good. Yeah, thank you so much. Okay, let me just check one more time. Might as well while we're here, right? Okay, I think we're good. Okay, perfect.
And apologies to those who admitted late. Blame it on Zoom. Blame it on the situation. Unsettling times. Apologies.
Blame it on me. Blame it on me.
No. You're doing great, James. Thank you.
Okay, so for those of you who just got here, we're all the way deep into Dask. Dask is a thing where you describe Python code to run, and it runs it in a special way. Okay, you're good. You're gonna pick it up as we go. Once Dask has arranged your work into this graph, next there's an optimization step. So I mentioned when we were talking about Spark that Dask doesn't have as powerful kind of high-level optimization steps as Spark, but it does still have some. It still has some ways to figure out that your graph could be reordered in a way that will reduce memory usage, that will reduce maybe the total runtime or something like that without sacrificing kind of the functional correctness. So there is some optimization that'll happen. After that, you reach the serialization step. So now after construction and optimization, you just have this like special Dasky dictionary that the scheduler and the workers will understand. That dictionary that includes your custom Python code, your functions, that thing has to be, written to bytes like pickled or cloud pickled and sent to all of the places where the scheduler and the workers are. So that's done in serialization. In scheduling, the scheduler describes the graph to the workers, and then it also tells each worker, okay, you're going to do this, and then come back to me and let me know when you can do another thing. And the worker does the thing, and then it's like, cool, you're done with this. Let me look at the graph. Okay, you're going to do this thing next. That decision is extremely complicated. The scheduler will make that decision not just based on, walking through this graph simply. It won't always give a worker the next task, but the scheduler might have other concerns like, preferring to give a worker a task that only needs data that's already sitting in memory on that worker to reduce communication or things like that. And then once everything's been scheduled, I kind of had already started describing this a little bit. You're into execution mode. So in execution mode, workers say, hey, scheduler, give me something to do. And the scheduler's like, do this, please, as fast as possible. And they do it. And then they tell the scheduler a couple things. They send their logs back to the scheduler and say like, hey, I'm still working on it. Here's some stuff that's going on. They send some basic information on like CPU utilization, memory usage, things like that. And then they send back task statuses. So they might tell the scheduler, I tried to do task 1, 2, 3, 4, 5, and it failed. Or I tried to do this task and it succeeded. And here's the ID you can use to reference the result of that task in memory, stuff like that. And so if you want, you can create these graphs yourself. using a module in the main Dask package called delayed. So this is a small snippet taken from the Dask docs. Imagine 3 very simple functions. One called inc that just adds 1 to a number, one called double that doubles a number, and one called add that takes in 2 numbers and returns the sum of those 2 numbers. You could write those as plain Python functions and then wrap them in this function called dask.delayed. There's also a Dask delayed decorator that you can use on those function definitions. And once this for loop is done, nothing will have been computed yet. No numbers will have been added, nothing will have been summed, but this graph that you see on the right will have been created. And it's not until you ask for the result of that, in this case by calling it on some data and assigning it, but you can also use a function called compute. It's not until you ask for the result that Dask will say, oh, James needs a result, let's get to work. And it starts doing the work. It goes through those processes that we talked about of scheduling and of execution. So if you want to write highly custom stuff, you can do it in Dask. You have as much control as you want to put things anywhere that you want on this task graph. And then Dask will handle distributing the work, monitoring resources. Dask will even handle automatically spilling data sets to disk if the workers are starting to run out of memory. But that's kind of scary, and it's like kind of a lot. And especially for, tasks that people have done a million times before you, training an SVM or like adding a column that's like the log of another column to a data frame. You shouldn't have to be writing your own stuff for this. And so that's where the next level of abstraction up comes in. And these are the Dask collections. So I want to talk about 3 of these: the Dask bag, the Dask array, and the Dask data frame. The Dask bag is kind of like an RDD in Spark. This is just an ordered collection of whatever data you want. And you can do things like map and filter and reduce. So think of this kind of like, if you're not familiar with RDD in Spark, this is kind of just like a list object or something like that in Python. The next data structure is an array. The array is meant to have an API that's extremely similar to NumPy, but it's broken up into multiple physical pieces. And I'll talk about that in a second. The third data structure that's really, really critical here is the Dask data frame. So the Dask data frame it has an API that's very similar to Pandas, but in reality, it's actually multiple small Pandas data frames kind of stitched back together. So you don't need to know how many of those pieces there are or that there even are pieces, but there are. And I think this is really well explained by this figure on the left. So this is another one of the figures that I took from like an issue or a pull request in Dask that was talking about some proposed new figures from one of the Dask maintainers. I really, really like this figure. And this describes the Dask array. So each of these kind of collections of blue boxes, those are NumPy arrays. And that pink box at the top is a Dask array. So let's look at this, right? On the left-hand side, you have a 6-element NumPy array. When you call, x.sum, NumPy is just going to march through those numbers, add them up, and return the sum, and you're done, right? If you instead had a Dask array representation of that data, that Dask array might actually be broken into 2 smaller NumPy arrays. So instead of a 6-element array, you have a 4-element NumPy array and a 2-element NumPy array that are maybe on different physical machines, or at least owned by different processes. And when you call .sum on a Dask array, it's going to go say, okay, whichever worker has the first chunk of this array, give me the sum of your piece. Whichever worker has the second chunk, give me the sum of your piece. And then I know I can sum those things back together and give James the sum of the entire array. That's the basic idea behind all of these data structures. But what's important is you can just use this .sum method just like you would in NumPy. You don't need to say, okay, this worker is at this IP address. Here's the address in memory. Like it has this many of the rows. Dask does all of that magic for you. Okay, this is a Chicago ML meetup, right? Let's start talking about machine learning finally here. Now that we've talked about how Dask does its work, we've talked about these Dask.
Wait 15 minutes?
Yeah, I'll tell her that you'll be available in about 15 minutes.
I think maybe one of you needs to be.
Yeah, you can preemptively mute anyone.
Oh, okay, thank you. And so now that we've talked about these collections, now that we've talked about these Dask data structures, let's talk about machine learning. The Dask ecosystem has a number of these packages that allow you to do distributed machine learning on Dask collections. So these look and feel like scikit-learn or maybe like other machine learning libraries that you're familiar with, but they take in Dask arrays and Dask data frames as their inputs. So one of these is called Dask ML. This is maintained inside the Dask project. And this has an interface that's very similar to scikit-learn. There are other projects that have adopted the ability to use Dask datasets. Two of them I've listed here are XGBoost and LightGBM. You may see this kind of like crossed out list of packages on here. There used to be a project called Dask XGBoost and another project called Dask LightGBM. Both of those projects do still technically exist, but their changes have been upstreamed into XGBoost and LightGBM respectively, and you should consider both of them kind of deprecated. There are other projects. There's a project from NVIDIA called QML, which lets you work on data structures that are kind of native to the GPU. So you're not shuffling data back and forth between GPU memory and main memory. These can also take in Dask data frames, a special type of Dask data frame that stores all of its data in GPU memory. So there are a couple of these extensions, but I hope that for those of you who are familiar with doing machine learning in Python, I hope that you look at this code on the right-hand side of the screen and think like, that's actually not that bad. That looks pretty similar to what I'm used to just doing without Dask. And that's really the magic of Dask. And then I want to be sure that I make this point. If you leave this talk and you're like, oh my God, this is so cool. I'm going to do LightGBM on Dask. I'm going to do XGBoost on Dask. You may Google around and you may find these projects, Dask XGBoost and Dask LightGBM. Like I just mentioned a minute ago, you should consider these projects deprecated. So the core core contents of Dask XGBoost were merged into XGBoost in August 2019, and the core contents of Dask LightGBM were merged into LightGBM about 3 months ago. So if you're writing new Dask machine learning code, you should have a preference for XGBoost and LightGBM, not for these old projects. So I just want to be sure that I make that really clear. Okay, with that, I want to go to a demo. I can see we have one person in the waiting room, so I'm going to go let them in. And I'm going to take a sip of water, and then we can get started. So while I do this, I'll leave this screen up. You can go to my GitHub, and you can find all of the code that I'm going to run next. Okay, great. Let's do it. So I've already kind of pre-baked my environment a little bit here. I'm sure maybe some of you have seen cooking shows where they're like, put the turkey in the oven and come back in 8 hours. And then it's like 5 minutes later and the turkey's there. I've already kind of got some stuff running here, but I promise you all of this will work based just on the code of my GitHub. And that code, by the way, it has a permissive, oh, we have one more waiting room person. It has a permissive open source license. You can take it, you can do whatever you want with it. And so this is just running, I'm just running a little notebook inside a container on my laptop. Okay, I'm going to show you two examples here. One of them takes a little bit longer to set up. So I'm going to get the AWS example started, show you some stuff on localhost, and then we'll go back to AWS. So in this example, I'm going to use a project called Dask Cloud Provider. Dask Cloud Provider is a library that has this collection of basically like helper functions and classes for setting up a Dask cluster on different public clouds. So the last time I checked, they had some support for AWS, Azure, Google Cloud, and DigitalOcean. And I think, adding more all the time. Okay, so I'm going to use a service called AWS Fargate here. I mentioned this earlier in the talk. Fargate is a container orchestration service from AWS. So basically, you tell it to run these things called tasks. You give it a container image and some specs like how much memory and CPU, and then it just runs a Docker daemon on some virtual machines, and it like runs your container in Docker. That's the basic idea. So I've imported Dask Cloud Provider. You can just pip install Dask Cloud Provider. Everything I'm showing you here is completely open source. Like you can use it today. I've already built these images and pushed them to the Amazon ECR public registry, but you can use any public image that you want. And I am going to kick up this cluster. Now this is going to take a couple minutes, but I'll just show you. I'm over here in the AWS console. I'm in US West 2. I don't have any clusters. If I refresh this page, now you should see I have a new ECS cluster. We are going to leave that for a few minutes, and we'll come back and check that out later. So let's work just on my laptop. In this example, I'm going to train a LightGBM model using Dask only on my laptop. And so Dask comes with this really nice feature called local cluster. And the local cluster is exactly what it sounds like. It's a Dask cluster that runs on your current machine. So in this case, I'm going to ask for 3 workers. And that means there's going to be a Dask scheduler process and 3 worker processes just running in this container that I'm in. And we can run that. Should just take a second. This cluster object, no matter how you create it, local, Fargate, Yarn, whatever you do, you're going to get a diagnostic dashboard that'll show you some information about what's happening in the cluster. And I actually want to split that out. And let's, oops. There you go. Okay, and let's make this a little bigger. That might be kind of hard to read. Okay, sorry about that. Let's just make sure we get this right. There you go. There's our diagnostic dashboard. Move that stuff over. All right, live demos, going great. So now we have our cluster. This is on my laptop. You can see that I have 3 workers. You know what? I'll just flip back and forth. I think that's just going to be easier. So you can see that I have 3 workers. All of them have an IP address of localhost. They're all right here hanging out. There are 9 threads available to this process, so each of them got 3, and they got a little bit of memory. Next, I'm going to just create some random array data using Dask array. This should look just like NumPy's np.random.random. And at this point, do you notice how fast that ran? That ran like really fast for a data set with 100 features and 1 million rows. I mean, I know that's not huge, but like it's kind of big, right? Well, I kind of cheated. The thing that's happening here is that the Dask array is a lazy data structure. So if I just print data, I'm not actually going to get an array printed. I'm just going to get this sort of metadata. When I say that this is a lazy data structure, this call that I made, it doesn't actually return an array of real values. It returns a Dask graph. And that Dask graph has a bunch of functions in it that are like, random sampling functions to create an array. And so what I'm going to do is persist that data. So calling persist says, all right, Dask, just start working on kind of chewing through that graph because I want to use that data. And once you're done with it, permanently keep it in memory in the cluster. So let's see if I can do this fast enough. I'm going to call persist. And now we have some stuff working. Okay, it ran really fast. But now we have some stuff working. You can see I got 20 of these tasks called random sample. This is some inner Dask function. And now you can see my workers have more stuff in memory. Before they had like around 50 megabytes of stuff in memory. And now we're around like, 200 to 300. Okay, cool. My data's ready to go. Now I'm going to use LightGBM. So I want to make an important point here. If you pip install or conda install LightGBM today, you're not going to have access to this Dask feature. This feature is kind of only available building from source. And it will be until we release LightGBM 3.2.0, which I'm not really sure when that'll be. Sometime, hopefully weeks, not months. But all of my sample code in that kind of repo that I set up for this talk that I'll link to again, you can just like run a couple commands and it'll install LightGBM in this image for you. So don't worry about it. You should see that these are just like kind of the common LightGBM parameters. And one of the most important things that I'm setting here is this parameter called tree learner data. So when you work with LightGBM on one machine, you never need to think about this parameter. This parameter is specific to distributed training. And this says, okay, I know you're going to have multiple workers. Will each worker have a subset of rows or will they have a subset of columns? So LightGBM distributed training can either, it's distributing the process of choosing splits for a tree. And it can either do that by distributing some of the kind of like the work of evaluating splits over multiple workers that have, all of the columns but a subset of rows, or it can distribute the work of creating basically feature histograms and like doing some other stuff over workers that have all rows but only some features. Don't worry if that didn't make sense. I'm intentionally going past that a little bit fast. Shouldn't be necessary to understand this. And in almost every use case, just use tree learner data and you'll be fine. So I'm going to fit this model. And now if we go back to my task graph, we should see some cool stuff. So we should see that we have 3 of these train part tasks. Let's see if I can get this fast enough. Here's each of my partitions. And then I'll see how quickly it went. And then at the end here, we had 3 tasks. That was 1 training contribution task per worker. So each worker starts up and is like, okay, I'm working on the training. I'm working on the training. They all communicate with each other and they all say like, here's what I think the best split is. Here's what I think the best split is. And they keep doing that until training stops. Training produces, let's just check our, training produces this object called a Dask LGBM regressor. This object is it's a different Dask object. However, it has inside of it the normal LightGBM scikit-learn regressor. So once you're done training, you can run 2 local, and you'll just have this model that you're used to getting from any experience you've had with LightGBM before. You can pickle this. You can whatever you were doing with LightGBM before, you can do with this. And what this means is you don't have to have Dask as a runtime dependency when you're doing scoring. So you can deploy this non-Dask model. You don't have to have Dask installed wherever you're doing scoring, and it'll just work. You can see that this model has the standard LightGBM booster in it. You can get a data frame representation of all the trees. And you can also use the Dask interface to predict on data. And you'll see these predictions, they return a Dask array, so they're lazy by default. But if you compute that, you'll see this was a binary classification task with random data. So that's why all this data looks like it's very, very close to 0.5. You can even have the Dask regressor, just like the regular LightGBM regressor, take advantage of this cool feature called predleaf, which says for this observation in my data, which node in each tree did that data fall into? Kind of interesting. But you can do all of that stuff with the Dask model object. So hopefully you see it kind of looks and feels just like using scikit-learn, and you have some nice tools available from Dask for kind of profiling that work and checking out what's going on. Okay, that's on your laptop. Let's go to AWS. Let's see how our stuff's doing over here. All right, if I look in my ECS cluster, now everything is running. This is great. I can go in here. Let's take a look. So I have 1 worker and 3 schedulers. I can go into this scheduler and look at the logs in AWS. And it's like, hey, just so you know, I have these workers. They're joining. They're doing stuff. Let's go back to my notebook. I'm going to show you training on AWS. So we're in here. We have our cluster. Everything's set up. I can go to this diagnostic dashboard. This is just like the one that I showed you before. Let's keep this here. Except this IP address is the IP address of a VM in AWS. So this is not on my laptop. Because it's not on my laptop, I can make this a lot bigger than my laptop, where I can get many of them put together. And let's run training. We're going to create our data exactly the same way. And now you can see stuff is going on. But again, none of this is on my laptop anymore. Only the notebook is on my laptop. We can get into our training, train our stuff out in AWS. If we refresh here, we should see some more interesting kind of LightGBM logs. Let's take a look. There's a couple of interesting things there. Training is running. You can see this nice task graph again. Almost done. And then at that point forward, from that point forward, once again, we just have a normal LightGBM model object. And this is all exactly the same stuff that I just showed you on my laptop. I know that I went through that very fast, but I hope that you saw that the code to run this on my laptop and the code to run this on AWS was almost identical. The only thing that was different was this little block here where we set up the cluster. So here I have this cluster set up with Fargate cluster from Dask Cloud Provider. Here in the local notebook, I use local cluster. But because Dask has this nice separation between client, scheduler, and the workers, none of my other code had to change. None of my other code had to know that it was on AWS. It was just like, I'm on a Dask cluster. I'm going to do a Dask clustery things. And before I forget, let me shut this cluster down so it doesn't cost me too much money. When you end the session that created a Dask Cloud Provider cluster, it will mostly tear everything down itself. So you should see now I only have the scheduler left. It'll wait a couple minutes to tear the scheduler down just to be sure that you wanted that. But I'm just going to go do that directly right now. And there we go. And that probably cost me like 30 cents for that 10-minute intro. Like not too bad at all. Okay, I know that was a lot. Let me just tell you a few more things, and then I'll open it up for Q&A. So first, I know that I went through the demo very quickly, but I want you to know you can try this demo yourself. You can go to this GitHub link on the left and get all of these notebooks. You can build these Docker images. Nothing here was proprietary. All of my talks are released under a very permissive open source license. Do whatever you want with them. I mean, please don't go give this exact talk with these slides and just like not say that it was my talk, but do anything you want. Use these notebooks as a starting point for your own projects at work or at school. Do anything you want. If you want to come try this out on larger machines, if you want to play with Dask on GPUs, if you want to play with Dask on machines that have, 256 gigs of RAM and 64 CPU cores or something like that, you can come to my company, Saturn Cloud. Sorry, I don't own the company. My employer, Saturn Cloud's website. We have a project called Saturn Cloud Community. It's absolutely free to get started. You can just come click buttons, try some example projects, and get familiar with Dask. So either of those will work for you. They're free ways to get more familiar with machine learning on Dask. With that, I want to thank you all so much for your attention. I know that it's a little bit of a long talk. Please feel free to reach out to me at any of these places. After the talk, I'm also happy to take Q&A right now. Thank you so much.
Thanks, James. That was great. I have a question.
Sure.
So let's say I have a machine with multiple GPUs and I want to configure the scheduler either at the delayed level or, does this mean I'm the host now? What happened? Something happened here.
Oh, I don't know.
So let's say okay. So I want to schedule a number of long-running operations, one to land on each of the respective GPUs, but I don't really care which one, as long as we don't get two assigned to the same GPU. In your experience, how well does that support in Dask?
Yeah. Okay.
For something like that, scheduling on a per resource basis.
And you said single machine, multi-GPU.
Yeah, a single machine,
okay.
Right.
So so the question was about using Dask for like a single machine, multi-GPU type of workload. I've found that experience to be fairly good. I mean, I've only tried that once or twice. NVIDIA has poured a lot of time and energy into the Dask ecosystem. So NVIDIA has done a lot of work to make cuDF, that's CUDF, for example, work transparently with either cuDF data frames or Dask cuDF data frames, where all of the data is living in GPU memory. They have a project called Dask cuDF. They have made all the I don't know if it's QML or QML, but CUML estimators. They can all take in Dask data structures. And when you spin up Dask workers, you can actually create labels on those workers that say like, this specific task needs to go to a worker with a GPU. And then Dask will like kind of parallelize those tasks over the workers that are known to the scheduler that have GPUs. Now, what I don't know, what I can't speak authoritatively to, is how well Dask manages minimizing the transfer of data between main memory and GPU memory. I can't speak authoritatively.
I wouldn't expect it to know about that, but I just want to run a process on it. I don't care about it's that really just a basic scheduling, like a most basic scheduling problem.
Yeah, that you totally can do in Dask, and that's because of that important feature that I mentioned near the beginning, that a Dask worker is not a machine, but it's just a process.
Yeah.
Hey, James, this is Ravi. I had a question. Is Matthew Rocklin still the maintainer for Dask?
So the question was, is Matt Rocklin still a maintainer for Dask? So first of all, I want to tell you all, if you don't know, that Matt Rocklin does have Chicago ties. He studied at the University of Chicago for a couple of years. I talked to him about a week ago, and he was telling me about his favorite piece of urban scrubland in Chicago. Just want to be sure everyone knows that. Matt is still heavily involved in the Dask community. He's still part of a group of active contributors and maintainers of the Dask ecosystem. He also has a company called Coiled Computing that does, I would say, similar things to what Saturn does. You know, we consider each other competitors. So he's still working on Dask every day, very involved. If you remember, I showed a slide where I showed the ecosystem of Dask projects, right? There's like a project for using Yarn as the scheduler for a Dask cluster. There's like a Kubernetes project, a Helm chart. Matt Rocklin does not have his hand in every one of those projects. So in Dask, you know, they have been really intentional about building a community of contributors so that there is delegation. Every month I join a Dask community call where most of the attendees, it's around 20 to 25 attendees, who are all Dask contributors. And people go around and they talk about what they're working on. And there is kind of a nice, you know, anybody can work on anything, but there is a nice delegation of like, people know who's working on the kind of data frame and machine learning types of things, and who's working on the sorts of, networking types of problems, and who's working on deployment, like Kubernetes problems and things like that. So long answer to your short question, Matt Rocklin is still very involved with the project, but I think if he was here, he would not be comfortable saying that he is the maintainer of Dask.
So I had a actually question. I started tinkering with Dask in February 2017, and I had a question on about Dask on Stack Overflow, and Matt Rocklin actually answered it. So just a little tidbit.
That's great. Yeah, there's been a really good. So I'll just tell you briefly. The company that I joined, Saturn Cloud, 10 months ago, they taught me Dask. I had never really used Dask before I joined there. And I told them when I interviewed, like, just so you know, I know you're a Dask company. I don't know Dask. And they said, no, that's fine. You know, we want to bring more people into the community who are not using Dask today. And I found that attitude in everyone in the Dask community that I've talked with. So you should expect that people that you consider to be big names in Dask are there grinding through GitHub issues, answering things on Stack Overflow, doing stuff like that. So it's been a really nice part of that experience.
Yeah, thank you.
So it seems like the presentation you gave is very close to like the architecture we have built in. Have you guys done any integrations with SageMaker or anything like that? Or
so the question was, have I seen Dask integrations with SageMaker, whether Saturn or otherwise? My short answer is no. The longer answer is SageMaker. I mean, I don't need to tell you, but I'll for the benefit of the audience that might have mixed SageMaker experience. The word SageMaker is actually like the top of a gigantic umbrella that encompasses a lot of services. So if you are just using SageMaker as a way to securely provision Jupyter notebooks in your AWS account on different types of hardware, you can use Dask transparently with SageMaker. You can write Dask code in SageMaker and connect to a cluster that's running in, Fargate or EKS or something like that and be fine. If you're using SageMaker as your, say, distributed training tool of choice for machine learning, and you're using like the SageMaker built-in TensorFlow or the SageMaker built-in XGBoost or Linear Learner or whatever, I don't know how much of a role Dask has to play there because SageMaker has done its own parallelization thing. You know what I mean? So I can't tell you there's like a really slick example I can point to that takes advantage of all of the strengths of Dask and all of the strengths of SageMaker, but I can think of a lot of, non-weird reasons that a team might use both. For example, there's a project that I really, really like called Prefect, which was created by some people from Airflow as kind of the successor to Airflow. That project is a workflow management thing just like Airflow. It expresses a directed acyclic graph of computation, but it has first-class support for using Dask as a way to actually execute all of that computation. So I could absolutely tell you about professional data science teams that use Prefect and Dask for like nightly jobs that do either scheduled scoring or batch preparation of features, and that use something other than Dask for training models. And that thing might be Kubeflow, it might be SageMaker, it might be whatever. Does that answer the question?
Yeah, it gives me food for thought because we're using Airflow as well, but it's sort of limiting in certain aspects. So it might help.
I think there's an opportunity there, but I think for specifically the things that I showed, so like the Dask XGBoost interface, for example, if you're doing XGBoost in SageMaker, you can either use that or you can use the SageMaker built-in XGBoost thing, but you're not going to like be able to use them together.
Okay, right on. Thank you.
Yeah, no problem. What else can I answer?
Oh yeah, I have a question.
Sure.
So let's say I have something that's not supported by, a higher level abstraction that's a library, ML library that's not already supported. And let's say I'm doing research and I want to sort of enable multi-machine distributed computation on my work.
Yeah.
In your experience, what's the process like in moving from single machine, single VM mentality, implementation, that sort of mindset, to a distributed implementation in Dask? How different is that, before and after, if you diff that code base, how different do they look? And how much sort of rethinking and fundamental paradigm shift do you think is required to make that move for somebody?
Yeah, that's a great question. And so the question was about, moving from single machine parallelized machine learning to like maybe multi-machine distributed machine learning with Dask. There are two different flavors of that. One is easier than the other. So the easy flavor is if you're used to using joblib with scikit-learn, you can plug in Dask right where joblib sits in scikit-learn. And what that means is like anything that has a scikit-learn interface, you'll be able to have Dask go train in parallel. But importantly, what that means is fitting multiple independent models to each other and then doing something with the result. So that's like, in Dask ML, there are these higher level classes. There's like a voting learner and an averaging learner and like an arbitrary combination learner. I don't remember the names, but those are all like, okay, I have my data split up into 5 chunks, like go train something on each of them and then ensemble together the results. If you're okay doing that sort of thing, it's a very, very low friction move from doing that with scikit-learn and joblib to doing that in Dask. But if instead you have something that's highly custom, like maybe not even highly custom, like let's say you're using Spacey and you wish that there was an implementation of Spacey's algorithms that took advantage of Dask, you're not necessarily going to be able to easily bolt Dask onto the top and get a lot of performance gains. Does that make sense? So like, remember I talked about how PyTorch, TensorFlow, LightGBM, and XGBoost, they have their own distributed training implementations, right? Those things are not just like training many independent small, let's say LightGBM models and then averaging them. That's like going all the way down to the level of everything that can be multi-threaded on one machine is now being done in parallel on multiple machines. So that's like almost a re-implementation of those algorithms. I think you'll find in the Dask ecosystem, there are not as many of those Dask native re-implementations of mainstream machine learning algorithms as you might find in like Spark MLlib. Does that answer the question?
Yeah, I mean, I think it's sort of the division between something easily parallelizable. MapReduce is an example of something that's a paradigm that you can throw a lot of things at. If you can fit something into one of the roll-up strategies, it's straightforward. If you need to go implement your own distributed algorithm, whatever that may be, then you're sort of in the weeds of that algorithm, and those are necessarily complicated. So
and I think if you're in that case where you're implementing, that Dask and Ray will be much better experiences for that than Spark. I mean, I think it will be good. It will be work. There won't be any magic there. Like something that is a for loop inside of a function called by a function in the public API of a library, you are going to need to go in and turn into
You just
a map of delay
sprinkle some decorators in there.
Yeah, for sure. But in Dask for sure, any arbitrary Python function, anything that can be pickled, you can distribute and run a bunch of them and do whatever. But I think that's the best answer that I can give to that.
So we had one question here in the notes or the chat. Just maybe a short comparison between Ray and Dask.
Sure. So I'll just tell you, first of all, my experience with Ray is limited to 2 conference workshops that I attended and about an hour of cumulative doc reading. So I am not an authority on Ray. Like, take this for what it is. Remember how I talked about how Dask is more flexible than Spark, and that is good for complex cases, but it means that you miss out on some high-level optimizations, right? Because there are less guardrails. My experience with Ray has been that Ray gives you even finer grain control than Dask, which lets you do more complicated things at the expense of more optimizations. So I don't know, for example, if there's actually a Ray, like a first-class Ray data frame object that will look and feel like a Pandas data frame. I don't know that. I think it's important to remember the history in these projects. When Dask started, Dask was not a machine learning project, right? Dask was a general purpose parallel computing in Python project. They had data frame support early on. They were really focused on that stuff. Ray started to enable reinforcement learning. So Ray started from this proposition that other parallelized Python types of systems were ill-suited to problems like reinforcement learning, where there are loops and there's like a lot of iteration and a lot of kind of arbitrary, complicated, sequential stuff. And so all of that is to say that Ray is cool, Dask is cool. If you already have a bunch of scikit-learn and pandas and numpy code, and you just want to use it on more data, or you want to do a larger group of experiments, I would try Dask before I would try Ray. But if you're in the case that Garrett was mentioning, that's like, I'm implementing something from scratch, and I just want it to all be in pure Python, and I want to distribute it, Dask and Ray, pick your poison. They both could be good for that.
I would be tempted to also consider the ecosystem that might be consuming your library, because I don't think, my impression is these are not overlapping ecosystems, so there's not interoperability. So you kind of land in a particular ecosystem with other interops and other libraries. So that, I think, would also be a consideration when you're looking to use one of these to implement something.
I think the place where you feel like you're in an ecosystem that you're coupled to is mainly around provisioning, and that's like that graphic I showed of like the scheduler and the workers. You're kind of, if you're a machine learning researcher, you probably are like you don't want to implement 5 different ways to just get like a scheduler that's talking over TCP sockets to a bunch of workers. Like, you want to focus on the data and the problem, right? So whatever Ray or Dask has available, and there are some like experimental projects, by the way, for running Ray on a Dask cluster and vice versa. So there are like some things. I think that's a place where you're going to have lock-in, and then you'll have lock-in in higher level libraries that you don't want to write yourself. So
yeah, this is what I'm talking. This is
right.
what I mean. I say ecosystem. I sort of mean that set of things that you tie to, the dependency trees that you get wired into, whether it be third party or not.
Yeah, that's true. Or like, right, there's all these data visualization libraries, like the HoloViz family of plotting libraries that work well with Dask. I don't know what their support is in Ray. But importantly, Dask and Ray do have a lot better experience, like a lower friction experience of, I have arbitrary Python functions, let me just pickle them and send them to data, than you find with like a PySpark UDF. So there is like a little bit less lock in there, but you're totally right. There's plotting libraries are choosing what to support. Machine learning libraries are choosing what to support. Like, there is an whole interesting world out there.
Right. Okay. If anyone has any other questions, feel free to ask them straight away or type them in, and I'll keep an eye on that. Otherwise, we will wrap up. Who's the person with the most distanced time zone? I I think we have a lot of Midwest Central Time Zone folk so far, I've heard. Maybe East with Florida. Anyone from out of you? Oh, I have Canada, so that could be, well, Montreal, it would be East. Anyone from Europe? Anyone from the Pacific side? No. So everyone's sort of, this is their evening. So the reason I ask is we have to say something. Some of these meetings can really be, it can be challenging to figure out what to actually say.
Sure.
All right, well, James, thank you so much. That was a really well prepared and articulate and terrifically informative presentation. And I'd encourage anyone who has further follow up just to reach out to I think he provided his contact info. I have recorded this. Hopefully it's going to work. So I'll post the link in the meetup. So if you want to circulate that amongst your friends. So with that, let's give James an actual live applause for his work here. Thank you, James. Come on. Unmute, everyone unmute. I want to hear those claps. Come on.
Thanks.
Thank you very much.
Just press the play button and have the virtual.
It's okay.
All right, we'll wrap this up, and everyone have a very, very pleasant rest of your evening.
All right. Thank you.
Thank you. Good night.
Bye all.
Thank you, James.
Thanks, James.